Hi everyone. In this video we continue our discussion of systems of linear equations with a focus on the process of row reduction, which is a method for solving an augmented matrix that comes from a system of linear equations. So we'll start with an example of a fully row reduced matrix in 4 variables. This matrix, this augmented matrix, corresponds to a system of linear equations that originally had 3 equations and 4 unknowns. And it's fully row reduced because we can see there is a leading 1 in the top left leading position, and that leading 1 is a happy leading 1. Above it and below it are all zeros. There's also a leading 1 in the bottom, in the position that's down and to the right by 1. And above it and below it are all zeros, so it's a happy leading 1 as well. Now there's no leading 1 down here. There's a 0 there, and that's okay. We don't need to have a leading 1 inside every single column, and sometimes we can't have a leading 1 in every column, or in every row for that matter. So that's fine, there's nothing wrong there. And because there's no leading 1 there, we can't use that leading 1 to zero out the numbers that are above and below it. So we would say that this matrix is as simplified as it can be, that we can't further solve or further reduce the matrix. What we have to do at this point is to state what the solutions are. So I'm showing this as a type of, I want to say a 90% goal, that if you're given a system of linear equations, once you get it down to this point, you have about 90% of the work done. We still have a little bit of work to do here. I'll show you what that work is. We have to state what the solutions are in terms of, in this case, we're going to have parameters. So what you do is the following. I'm going to label each column with its variable label on top. This is a process I recommend that you follow. x1, x2, x3, and x4. And then in every column that contains a leading 1, I don't need to put a parameter. In every column that does not contain a leading 1, I do need to put a parameter. So there's a leading 1 in the first column. There's a leading 1 in the second column. But there's no leading 1 in the third column. Remember, a leading 1 is the first non-zero number in that row, in that position. So this is, when I'm circling here, that's not a leading 1. It's not the first non-zero number in a row. So there's no leading 1 here. I'm going to put a t, parameter t for that column, because there's no leading 1 in that column. And then in the next column over, also there's no leading 1. There's no first non-zero number in the row that's a 1. So I'm going to put in another parameter here. So I'll highlight those as leading 1s. And then these are parameter columns. Because these columns do not have a leading 1. Okay, so that's kind of the first step. I'll embed all of that as a step 1. Now step 2, once we've done our labeling and identified which columns have parameters and which columns don't have parameters, and we know what we're calling our variables, in this case x1, x2, x3, and x4, what we do next is we translate each non-zero row into SLE format. So recall, we can translate from system of linear equations into a matrix by just extracting the coefficients and writing them. Well, now we're going to work backwards. We're going to put each row into like a 3x plus 4y plus 7z is equal to 10. We're going to write it in that format. So the first row, row 1, it says the following. It says that 1 times x1 plus 2 times x3 plus 1 times x4 equals 9. But we use the parameters t and r. For x3 and x4. So I'm going to rewrite this as x1 is equal to 9 minus 2 times x3, so 2 times t, minus r. And that's my solution for x1. I can state what x1 is in terms of those parameters t and r. So essentially I can pick anything I want for t and r, but then it tells me what x1 is in terms of those choices. For row 2, it says the following. It says that x2 plus x3 plus 5x4 is equal to minus 5. So what happens here? I want to do something similar. I want to isolate for x2, and I'm going to rewrite it in terms of t and r. So x3, I'm going to subtract that from both sides and replace it with a t. And 5x4, I'm going to subtract that from both sides, and I'm going to replace that with a r, so minus 5 times r. Now, we have 4 variables. We have x1, x2, x3, and x4. We have to make a statement about what x3 is equal to and what x4 is equal to, and in a sense we already did. We said that x3, its column was equal to t, and x4, its column is equal to r. So what that means is that x3 is equal to t, and x4 is equal to r. And maybe I'll make those color-coded so it matches what we have above. And now step 4, I'm going to make or step 3 rather, I'm going to make a final statement. We'll conclude that our solution vector x1, comma x2, comma x3, comma x4 is equal to 9 minus 2t minus r, comma, minus 5 minus t minus 5r, comma, t, comma, r. It's fairly involved. So maybe I lied when I said that we were done 90% of the work by the time we row reduced the matrix. Maybe we were only done 50% of the work. It depends on how much work was necessary to get the original system of linear equations into this row reduced form. Let's look at a second example. State all the solutions to this one. This one looks like it's worse, so you compare. This one has 3 equations with 4 unknowns. This one has 4 equations with 4 unknowns, so maybe we have some more work to do. But look at it very closely. We could start translating and say, well, first of all, that it is row reduced, but we could start translating and say that row 1 says that x1 plus 2x4 equals 5. So maybe we'll let x4, that column equal t. Then x2 plus 3t is equal to 6, and then rearrange. And then x3 plus 4t is equal to 7, and then rearrange. But we don't have to do that. Look at the 4th row. So this is the best thing that can happen to you when you're solving this type of an artificial system of linear equations. If you ever see a row that looks like row 4 here, notice this row. What does this row say? So if you were to write this row in linear equation form, it says the following. It says 0x1 plus 0x2 plus 0x3 plus 0x4 equals 8. for some values of x1, x2, x3, and x4. Can you put numbers in there that will make that true? They'll make left-hand side equal right-hand side? Because you're going to have 0 times whatever you put for x1 plus 0 times whatever you put for x2 plus 0 times whatever you put for x3 plus 0 times whatever you put for x4 somehow equaling 8. It's not going to happen. Never. This is impossible. This is impossible. Since 0 times anything is equal to 0. I should say any constant or any scalar. There's need to put a little vector symbol above it because 0 times any vector is a 0 vector of the same size, but we're talking about scalars here, constants. 0 times 5 is 0, 0 times 7 is 0. So what does this mean? What is this last row telling us? It's telling us that there's no solution. No solution to the SLE. And we don't have that. We don't even have to look at the other rows. It's not necessary. One row that has this fatal flaw, 0, 0, 0 on the left side, and then not 0 on the right-hand side, it automatically means that there's no solution. Now look at the previous example. We had a row that was all zeros and it didn't cause any concern because that bottom row says that 0x1 plus 0x2 plus 0x3 plus 0x4 is equal to 0, which makes total sense. It's not saying anything that's ridiculous. Whereas in this case, this statement is ridiculous. 0 times a bunch of stuff gives you something that isn't 0. Impossible. We'll pick up on the row reduction process in the next video.